Hi everyone, we will now talk about the load flow and power flow topic in this course. And we'll first start in chapter 6 and go over to chapter 7. Those chapters are very close linked, so we need to understand some of the stuff in the chapter 6 to actually go into work with the load flow problem in chapter 7. So the load flow is the most important network calculation, as it allows insight into the steady state behavior of the power system. So this is very important. We are not working now with transient dynamic systems, but we are looking like a snapshot of the flow of power in the grid with a steady state, as I say it. We also should remember that the equations for load flow becomes nonlinear equations, and we often have to linearize. So in every node, we can say in the grid system, we have a relationship. It can look something like this, where we have the voltage and the active power. And we typically have a relationship looking like this, a nonlinear curve with actually a maximum limit. This is something we will come back to when we work with voltage control problems. But remember that this is, it will look something like this. It becomes a nonlinear system. So when we're doing then the linearization, we typically like, if you do a load flow problem at this point, and we can have then a linearization at this point. Of course, we will come back to that in this area here, for example, we don't have like a feasible solution. We only will have feasible solutions on this side of this curve. This we call the PV curve, but the only point for now is just that you understand that this is a nonlinear relationship. That's why we need iterative methods. Another important issue for doing this load flow is this n-1 evaluation. So if we call this a bus bar, this here, and you have then a flow of power coming through into this grid, and then we have, let's say we have 3 lines going out from the same connection point. Then this power delivered should then, even though we have, if this is, here is n is equal to, let's see, 3, and we call it n-1 criteria. That means even though one of these lines goes out of service, the rest of the residue of the lines should carry the load flow. And sometimes they also could have, for example, they want to have even more safety in the system, and we should probably have n-2. That is also sometimes they are checking. So this is also a very important criteria. Another thing is that the node voltage, if we call this here, if this is a node in a bus system, we have actually some kind of constraints on this with the voltage level. We say typically that between, if this is this point here, and let's see, if this is 1 per unit, this point in the voltage, we say typically that the voltage level should be between 1.1 and 0.9. So the voltage should lay in that range. So this is also a typical constraint for the grid system. So when we do this load flow computation, we have some input. We need a network topology and network parameters for the calculation, and we need also node information. And as I said, node is typically what is a bus bar in the grid, but typically we just denote it as 1 and 2 and so on. And out we calculate node voltages, and we now have branch currents, for example, branch powers, and of course power losses is important. Generate the reactive power, and also what we call a slack node power. This is things we are calculating from the load flow. Here you can see a snapshot from a load flow program. This is from the PCC from Siemens. You will use another one in this course called Power Factory or DG Silent. And as you can see here, of course, they can show us, for example, here that which way the power is flowing from here. We can see that in this case, in this line, we have 42 megawatt flowing this way, and we have 26.3 megavoltage ampere reactive flowing also in this direction. And we can also, and that is from this bus bar called Svelgfoss. So this is how we can indicate which way the power is flowing. You can see that this arrow goes in one goes to one way and the other direction. Here you can also indicate it like how much the line is loaded. So this is like 34% loaded. And also you can get the indication like here that this is like 0.9 per unit voltage. And it's yeah, and then you have gives like equivalent 120 kV. You also get like a column map. You can see over here when it's much more highly loaded. We need to let's see, take this away. We will have like a red color. It means that in this area we typically have a higher loaded lines delivering the power. So this first lecture is from the chapter 6, and it's called the network calculations. And what is important here is what I've highlighted here. The 6.1 here, the nodal analysis and admittance matrix is of course important. And also this 6.3, the bus impedance matrix. These 6.4, 6.5, and 6.6, as I show here, these you will come back to when you use in the fault analysis. So I'll just briefly touch it in a small video here. Yeah, and this last one, this 6.7 and 6.8, and this one, those are more methods for calculating this set bus matrix. So it's more like a matrix techniques. We don't use so much time in this course for this. This is more if you take like a special course in matrix techniques, you will will typically learn more about it, such like triangular factorization and power invariant transformations. Also you have this chapter of the node elimination background reduction. That is also more like a technique, but so we will briefly just talk about it, but focus on the 6.1, 6.3 mainly from this chapter. So let's start with this nodal analysis and admittance matrix. And of course, it is maybe more traditional to work with the impedance matrix. You can see on the left side here, we can represent the voltage source with an impedance, as you can see here. And let's see here. And then we have the ES is equal to the voltage drop or impedance. And of course, it will be the sum here for the voltage. So here's an, but more often we're using the admittance version, as you can see here, where we have the representing as a current source inside. And we can then use the node analysis much more efficient when we have then the IS is equal then to the current here, I, plus the current through the admittance now here. And it becomes in this fashion. And this is the way we're going to use it when we do calculations now. And by doing this, we can have then the voltage, the node voltage becomes then the variables that we are actually solving for. The nodal analysis and admittance matrix have some rules when you develop this Y matrix or admittance matrix, as is mentioned here. We often call it then the Y bus, as mentioned here, and the rules are, the first one is that the diagonal element, the YJJ, with the subscription JJ, it means that when we have what we call a self admittance on the diagonals, it will equal the sum of the admittance directly connected to the node J. So that's the one first rule. The other is that the off-diagonal element Y and subscription IJ equals the negative of the net admittance connected between nodes I and J. We will of course look a little bit more detail on this later, but if you see on this in this matrix here below, here you can see like a 4x4 matrix, and you probably know that this looks familiar, for you have learned about the AX equal B. So where you have then this is the A, this is the X, and the B vector. And this, when we put it in this fashion, we can of course solve this in the X, and we can have the inverse of the A matrix B if it's invertible. So this is something you probably have seen before, but now we're using this in the electrical equations. So in the on this first rule where you have the diagonal elements, that means these elements on the diagonal, the 1, 1, 2, 2, 3, 3, and 4, 4. So this means that it is a 4 nodes plus reference bus is denoted like this. And then we have the off diagonals. So as you mentioned, all this rest here of diagonals here. So this is a special way to actually construct these matrices. And of course, we have then the X vector is now the voltages, the variables, and the B vector is now the currents. The self-admittances, we call it, is highlighted here, the self-admittance. This on the diagonal, you can see here. And the off-diagonal admittances are then the mutual values here. And this is, of course, as you said, here you have Y between 2, 1, Y 3, 2. So you can actually like follow, you see the first, if you look at the first one here, VY 3, 2, for example. Okay, let's erase this again, take it away. So let's see if we take this Y, okay, let's take this one, Y 1, 2. So the first subscription 1 is then related to this one, the row, and then the second is then related to the column. This is column 2, row 1. So this is the position. So try to refresh this how we work with matrices. So some authors call the self and mutual admittances for the nodes the driving point, another stuff, and also the transfer admittances. So this is another way to mention it. We call also the principal diagonal, and we call this a symmetric square matrix. So it gives a 4x4, and it's symmetric. It's also important. Another thing is that the bus admittance matrix, when it becomes very large scale interconnected power system, we will see after a while that it becomes many elements will be 0 elements, and we call this that is very sparse. It's sparse matrices, and this actually does that we can do some techniques to remove actually elements that we know become 0. So here is some information in the matrix. The work entailed in constructing Z bus is much greater than required to construct Y bus. But, this is what we're working with, but the information content of the bus impedance matrix is far greater than the Y bus. So when we work on short circuit calculation, when we have a ground to phase fault and so on, we will have much more information when we're using the set bus, and so we use that instead of the Y bus. We'll come back to that. Unlike set Y bus, the bus impedance matrix of an interconnect system is never sparse. So when we work with the impedance bus, when a system is regarded as being subdivided into independent parts by open circuits. This will become much more clear when we do examples. So we can apply this 4x4 matrix on this feature 6.6 show the diagram. So let's now you see now it's denoted and the YB, YC, YD, and so on. And let's put all of this into this matrix. How can we do it? So let's start on this first one. If we now take the position of 1, 1, the self, we now know it's the sum of all the nodes, the admittance connected to the node. So for example, if you look at the first, this Y1, 1, we can stand now here in this position, in this bus, and we actually stand here and see what are actually connected to this node. And then we can of course see 3 directions. We have the 1 to 2, the YC, 1 to 3, YC, 1 to 2, YD, and 1 to 4, the YF. And then you can see you sum all this admittance in that position in itself. The same you do for the position of bus 2. So here you also are standing there and looking then the YB, the YD, and the YE. And then thirdly, you are on the third bus standing here. Then the same, you have the YA is here, YB we already have, and the YC from this, and so forth. Now look at the off-diagonal elements. So if we start on the first one with the Y1, 2 here, we can then see between bus 1, now standing on bus 1, 2, 2, we have YD, and we get a negative sign here. So in the same way we are doing now for between 1 and 3, we get minus YC. Between 1 and 4, we get minus YF, and so on. And we can also see that we have some zeros here, because now we have some open also. But this is between, if you look at bus 3 and 4, for example, here, and you can see there are no directly connecting here. It's just like the reference node. So it open on this side, so it becomes 0. The same here for the 4, 3, and 3, 4. So in both ways you can see it becomes 0 here. So here can a small indication of that the matrix becomes some kind of sparse, as you see. Yes, and of course in the same way we will have then here the X vector, and this will be then the voltage related to the node 1. And 2 and 3 and 4, and it will of course equal the currents of the circuit here. So these will be the voltages and the currents. And now you have to go through another 2 videos. We will have one where we will look at this generic outline of the network calculations. So we have a video going through this system, as you can see here. And after that, we will also have an example. You will go through both by hand and also in MATLAB.